So I wanted to give a short introduction, and this is a very pretentious title. I'm not going to answer that, but I don't know. We felt that during the last summer school, it was always nice to not be me dive into technical details, but start a little bit more high level to set the scene. And I'm going to try to do this in the next 70 minutes, hopefully. And both I'll talk about some basic ideas of learning and inference, but also about some aspects with history that I find interesting. And of course, this is always very subjective. Now, maybe as some background, why are we here and why do we do machine learning here? So this is the Max Planck Institute for Intelligent Systems. And we are interested in understanding the organizing principles of underlying complex intelligent behavior. And on these videos, you see various such behaviors of levels of complexity. You see a white blood cell in pursuit of bacteria. This is a frog trying to catch some insect. A human doing parkour. Here's engaging in a complex form of behavior. So all these things are difficult, and if one tries to understand them, when try to do it the biological way of analyzing these systems in as much detail as possible. But the physics point of view is a little different. In physics, we try to build generative models that explain the data, or try to build, I should say generative, or it sounds like gene. We try to build detailed models that understand or create phenomena that we observe. This is actually a picture of Richard Feynman's blackboard, photographed after his death. So that's part of his legacy. He says, what I cannot create, I do not understand. So a lot of people in robotics take this as their motto. Use as physically create. Feynman probably didn't mean it like this. He meant to say, well, whenever he reads a paper, he wants to be able to create it himself or do every step himself. He wants to understand everything in detail. And actually, I think that's also a motto for research. It's not enough to skim through something. You want to be creative and do something on top of it. You really have to get into detail and try to understand it better than the authors' paper understood it themselves. Now, I showed you all these complicated behaviors. Of course, we are far from recreating most of this in synthetic systems, but we can do some simple things. Here's one example of a simple thing we can do. We already had a talk about Amazon yesterday, so this is my favorite Amazon example. If you go to the German Amazon website and you search for this thing called a glass Schneider, so a glass cutter, the device you attach to a window pane and make a round hole, then Amazon is going to recommend some other things go along with it. Now this is a year old, or maybe 2 years, and I have this talk at the opening of the Amazon lab in Berlin, so maybe it doesn't work anymore. Maybe it's possible that they changed something, but here they recommend baklava, and here's some baseball bats. And this is the best one. That's a Batman rucksack with bat wings. So maybe some people think these wings work. Anyway, so all this is, of course, based on machine learning and empirical inference. So I use empirical inference as a somewhat broader term that includes not only learning but also inference. And of course, we deal with data. For instance, if we are scientists, let's say we're physicists, we might measure these data points of two observables, and we think we're good at scientific inference. And in this case, we probably say, yeah, that looks like there's a linear relationship. But of course, in principle, could also be something more complicated. And there's this thought experiment pointed out by Leibniz, who said that, well, if I take my fountain pen, dip it into the ink, and then I just splash it over the piece of paper, I get some random dots. I will also be able to explain these random dots mathematically, which then begs the question, which of these explanations we would be able to call a law. What's a law of nature if we somehow mathematically can explain everything, and maybe it's just a matter of how the explanation looks. And Leibniz already had this intuition that we would call it a law of nature and only if the equation is simple in some sense, which then of course leads to the question, when is an equation simple? What does it makes it simple? And we have so far that learning theory that's probably addressed this in some form. And a number of people have thought about this issue, and I've listed some of them down here. Now, this was the point of view of Leibniz, one could view as a mathematician and philosopher. Here's a different point of view. That's a physicist, Rutherford. He said that if your experiment needs statistics, you ought to have done a better experiment. So if you need to do anything complicated with your data, then you have the wrong data. That you have to think cleverly about what kind of data you should get, and then the inference should be trivial or obvious. I think we are all in machine learning. We don't believe in it. So we like to look at non-trivial inference problems. And actually, non-trivial inference problems, they are all over the place. For instance, if you look at perception, so we are all pretty good at recognizing handwritten digits. So a set of digits here with a corresponding class. We can recognize them all. So these are just 8s and 9s. So this looks like a simple inference problem, but if I just apply a fixed permutation to these pixels, so mathematically I have just to change the basis in which I express the data, so there's still the same information content there, then these patterns look much harder to recognize for us. Of course, the reason is, or maybe the main reason is that we've been trained on this kind of data for a long time, but we haven't been trained on this kind of data. So maybe the problem isn't actually that trivial. It just looks trivial to us because we've already seen a lot of training data. So biology is full of non-trivial inference problems, and machine learning is also full of them. And this used to be my example of a large-scale machine learning problem. It's probably not large-scale anymore. So this was a study I was involved in 10 years ago, and there we had 15 million training points, which we thought is huge. Now people are probably laughing about that. It was a problem from a classification problem based on DNA sequence data, and we had to classify them into classes using a data set. This is the number of training points, so that's a learning curve. Here it goes up to 10 millions. We actually have 15 millions. It is the precision recall curve, and the details don't matter. But interesting thing is, at the end, we get a very respectable performance. This was actually state of the art at the time. Once we have millions of training points, but if we only have hundreds or thousands, we are almost at chance level. So this is a kind of, there's a dependence there. We can learn in the limit, but if we only look at 1,000 examples, we can't learn it. And most likely, if a human were to look at data at 1,000 examples, we also wouldn't find structure. So this is, it's a non-trivial inference problem. It wouldn't be obvious to us when we look at data. Probably we wouldn't be able to look at more than 1,000 points. We would get bored or just we're not built for this kind of data. So there is structure out there in the world that machines can find that humans can't find. So I find that that's more exciting even than winning against the chess world champion or in other games. It's a lot restricted to the domain. So we have this kind of superhuman intelligence or superhuman pattern recognition capabilities in some domains already for a while. This is 10 years old. And these kind of non-trivial inference problems, they usually have several characteristics. They're high-dimensional. The regularities are complex in various forms. This is non-linear. We have little prior knowledge, so we haven't been trained on this kind of data before. We don't have a mechanistic model for the data. And as a consequence of these characteristics, we need big data sets. One thing to keep in mind, and maybe that's also going to show up in the learning theory course, is that in the limit, we do know that we have methods that are universally consistent. So if we have unlimited data, then and we're willing to wait for an unlimited amount of time, we can achieve the optimal performance. And of course, optimal may often be better than humans. It's never worse than a human with the same information, but it may well be better. In this case, certainly is better. So from that point of view, it's not surprising that in certain settings we can get so much performance. And I think now the industry is realizing that, and we have learning methods that scale well large data sets, such as gradient-based learning, and large function classes, so deep learning and other stuff. But the small print people usually don't talk about. And one of the things in the small print is that this refers to an IID set, so identically distributed data. So we need data that's really from the problem that we want to test on afterwards. And we have, as much as we have developed machine learning, we have also developed methods for collecting data, collecting IID data, and all the large companies, they are paying people as labelers who create label data from the right distribution. So at search companies, they pay people to rank search results, etc., to make sure they have the right kind of training data. And violations of the IID setting make the problem harder, and this then ties into something I talked about this afternoon in causality. Anyway, so yeah, it's also so one of the crucial problems of machine learning is generalization, and most of you heard about that. So one form or one simple way to think about the problem is the number sequences. So suppose we see this number sequence here. Maybe you already thought about it. Guesses what's the next number? 11 or 12? Any other? 14 is also fine. So 11 is maybe the simplest one. It even has a name. It's the so-called lazy caterer sequence. Because if you take a piece of cake and you want to cut it into the maximum number of pieces, not necessarily of equal size, then this is what you get, because you just have to make sure that every cut intersects all previous cuts. So then so you add n pieces intersecting previous cuts. So that's a good solution. Someone said 12. That's also good. 13 is the Fibonacci sequence. 14. Sequence of divisors of 28, which actually ends here. If the person who said 14 also predicted that. I remember Olivier Bousquet, who at the time was also here as a postdoc in my lab. He's going to teach a course, teaching a course at this machine summer school. They know obviously it's a decimal expansions of I and E interleaved. And you could argue you don't even need, you just, if you take the decimal expansion of pi, you just have to look at the right position and find the sequence, and it tells you how to continue. Anyway, so there's this website where you enter these numbers and you get a lot of hits that are meaningful, and then you can ask yourself the question, which of these continuations is correct? And obviously, this question doesn't make sense. So there's no way to tell, and the philosophers have thought about this for centuries. It's called the action problem. It's considered an unsolved problem in philosophy. Smart people have thought about that. But the question in statistical learning theory maybe is slightly different. It's not about whether that one continuation is correct, but whether there are methods that we apply these methods, we probably arrive at valid conclusions. So it's a methodological question. How do we come up with laws that probably generalize? And this is, it also has a name in philosophy. It's called demarcation. Popper thought about this in detail. Bachelor of Science, Popper. He called this Kant's demarcation. So attributed to Kant, I don't know, Kant called it the demarcation problem. But it's called demarcation because it sort of finds what's the difference between physics and metaphysics. So what kind of methods does a discipline have to apply in order to be allowed to physics or to be in the physics section of the library. So someone once told me that the term metaphysics just comes from the fact that they placed it in a different part of the library. Someone speaks Greek. What does meta mean? Side or beyond. Okay, so it's beyond physics. Okay. So moving to the history of machine learning, and so this is a slide I downloaded last time. It's out of date, but it was already out of date. I mean, it's always going to be out of date. So this is from this text, our data mining history of machine learning. So that's the history of machine learning from the point of view of data mining. So it started with the neural nets, then decision trees came, neural nets came back propagation, SVMs, logistic regression. So now the world is logistic regression. This is the data mining point of view. In the next 20 minutes or so, I will try to give you the machine learning or neural nets or pattern recognition point. And that's of course a bit different. And in my personal view, the starting point was actually cybernetics. I really like this term, cybernetics, and the field of cybernetics. I started my career at the Maybury Institute for Biological Cybernetics, and I actually think we are currently, experiencing this technical problem. So what we're experiencing is actually not the digital revolution, but the cybernetic revolution. Okay. And it started in the 1950s. Some of the early people were Norbert Wiener, Neumann, Alan Turing, Claude Shannon. So Turing, I was at booking of Turing Institute last year. There was the grandniece of Turing. She said, should tell everybody, it's not Turing, it's Turing. I'm trying to get it right. These were the fathers of cybernetics. And cybernetics is about the study of control and information processing rather than just energy processing. So that was a paradigm shift that can't understand an animal or a machine or a human if you just worry about how it processes energy. It's this information, and it's obviously about as an information processing device, and you can understand a computer. Maybe you can't build one, but you can understand a computer without talking about energy, I guess. But you can't understand about information. And one of the early meetings that was the Bayesian conferences, the meetings, titled Circular Causal and Feedback Mechanisms in Biological and Social Systems. This was the birth of both cybernetics and probably also of cognitive science. And I found this on the web. It was a piece of paper that Warren McCulloch used to plan the Macy conference of 1953. It's quite interesting. If maybe you can't read the names from the facts. Bateson, McCulloch, Savage. Then what I found is Turing. No, no income. Piaget. Claude Shannon was listed as one of the alternates. So it sounds like if the other guys don't have time, let's get this guy Shannon. So Dr. Claude Shannon looks at the Bell telephone. This is the letter from Turing. Provide very gratifying and tempting to get your invitation. And he says, if it were in Europe, I should certainly try to make it. But I am really rather a stay-at-home type. So cybernetics, they try to understand humans, animals, machines, social systems in terms of feedback loops and control loops. This is a spaceship. This is an animal trying to get some food. This is some control. Of blood gas in the blood is a control loop. in the kitchen. So they tried to organize this. It very much looks like a picture from that time. And they try to understand everything in terms this is some kind of flow for voting or democracy, or how to build more modern government forms. And they had an experiment that lasted for a few years in Chile, in the Allende government. The famous cybernetician Stafford Beer was involved with them. They built this control room, and they were trying to control their economy of democracy in modern ways. So people were very optimistic about what could be done in cybernetics, how it's going to change them. And in a sense, they're right. I mean, because now look at how all these things that we have now are starting to change the world and even change democracies. And this seems to be happening, only it took much longer than before. So a lot of the ideas were there, but now it's 60 years later. So one of the early things that people studied were neural nets, and McCulloch was one of the fathers of the McCulloch model. They studied neurons formally and try to explain how the logical formulas can be built neurons. Showed that the networks can be universal machines, etc. There was Donald Hebb, he considered the father of connectionism. But there's also other early work related to brain theory, in terms of formal neurons, Ashby. The first piece of work, and the one that I want to talk about a little bit in more detail, is the Perceptron, which is close in spirit to what we now do in neural networks. This was developed by Frank Rosenblatt, who was a psychologist born in New York City. And he built the first perceptron, which is the perceptron. It was a physical device at Cornell University in 1960. It was the first computer that could learn skills by trial and error using a type of that was viewed as simulating thought processes. So psychological understanding, interested in understanding thought, and it was probably a very interesting time. He was apparently teaching an interdisciplinary undergraduate course, name of theory of brain mechanisms, and students from engineering and liberal arts, and Bayesian was quite a flamboyant figure talking about all sorts of things that he would apply this to, ranging from experimental brain surgery on patients to digital circuits that model various details of neuronal behavior, etc. So this was an interesting time, and he was also playing the press to some extent, and they had a big press conference together with the Office of Naval Research that was sponsoring his work in 1958, and this is the article in the New York Times, and reporting about this press conference, and he says, the Navy revealed the embryo of an electronic data that it expects will be able to walk, talk, see, write, reproduce itself, and conscious of its existence. It's nice how they put that all into one sentence and then sort of report it matter-of-factly as a piece of news. And then they talk about what Rosenblatt expects perceptrons will be able to do. So here towards the end they say later perceptrons, so not yet, but in the future, will be able to recognize people, call out their names, and translate speech in one language to speech in another language. Rosenblatt said in principle it would be possible to build brains that reproduce themselves assembly line. So assembly lines, but there was something modern in those days, and which would be conscious of their existence. So I imagine these were quite bold predictions, and these predictions also annoyed some. But it's still quite remarkable that some of these things you would say have now been realized. So they were bold, but not completely off. And among the people who got annoyed were Minsky and Papert at MIT. They were much more theoretically inclined, mathematically stronger than but it like was fuss about some considerable. They were annoyed that a lot of people were starting to work on this. They said, perhaps as many as 100 groups experimenting with the model either as a learning machine or in the guise of adaptive self-organizing networks or automatic control systems. So this is a picture of the perceptron. So the perceptron had something they call the internal retina. Then they had this layer of weights going to the so-called association units. In the first perceptron, each association unit was looking at 6 patches or 6 pixels on the retina. And this first layer was randomly wired. So 6 random connections coming in, these association units, and then we have the second layer units. And these second layer units were modifiable, and that was the revolutionary thing. These modifiable based on an error signal on training data. These were probably also the first occurrence of now called minimization in machine learning. And they were modified based on the perceptron learning rule. And then not long after, Novikov, it's a Russian name, but he worked in America, proved mathematical results, created a lot of excitement. Convergence theorem, yeah, probably know it, or otherwise, or you might see the learning theory talk. It's a statement about under certain assumptions this learning process terminates, and it's correctly classified. So if there's a margin of separation, well, actually, I think this one might not. You can write it in different forms. Anyway. This was great, but also people were aware that there are some tasks that cannot be done. So people understood that you can with one layer, but for a logical OR, XOR, exclusive OR, you need a cascade, some multiple layers or immediate neurons. And people knew that this is necessary, but they didn't have a training algorithm how to modify or how to learn the weights for this, and Rosenblatt recognized various limitations of perceptron. Sometimes it took long to learn, yes, especially in his physical perceptron. But there were also some tasks that are also kind of related to this XOR problem, nonlinear tasks that couldn't easily be learned. It didn't have a training algorithm, multi-layer systems. So there were various things, and so this is just a starting point. But then Minsky paper zoomed in on the weaknesses of the perceptron. So they wrote this book, or initially it was some kind of paper draft, which was circulated to their friends. It was very negative. Apparently later it was de-venomenized and published as a book. But they really thought that most of his writings without scientific value. And they became involved with somewhat therapeutic propulsion, dispel first shadows of a holistic or gestalt misconception that threatened to haunt the field of engineering and artificial intelligence. So they would be really quite shocked to see what's happening now, that going back to deep learning and it's heuristic. We have this sort of embeddings in high-dimensional spaces that become semantic by the means of having a large training set, etc. So this is exactly the kind of stuff they didn't want to happen, and they wanted to still feel clear of this danger, and they succeeded for a while. Anyway, so they analyzed the one-layer version, but they kind of they mentioned there's also the many-layered thing. They consider it an important research problem to elucidate or reject their intuitive judgment that this extension is sterile. So it's not interesting to multi-layer versions. Anyway, yeah, I think I've already talked about all this. So what does the Perceptron book do? Well, so they assume one output neuron, they restrict the order of association units. So the order means how many pixels on the retina association units connect to. This was important for them because the connectionist dogma was that this is somehow different from serial. This is parallel processing, and if all of these neurons, you have to look at everything, they felt that this is not an efficient way to parallelize these. So each of them was only looking at a subset, and then they proved that a parity, generalized XOR, cannot be learned unless the order of these association units is as large as the retina. They also had some statements about ground separation, issues of connectedness. And then, of course, in addition, they point out that the parity is pretty easy if you're allowed to use a serial algorithm. So this shows that it's much better serial processing. Now, one can debate about how important parity is found if you are trying to build a model of the brain or of a human. So, for instance, if I show you this picture here and ask you what's the parity of this picture, so is there an even or an odd number of black pixels? One of you is going to be able to tell me. So our visual system doesn't seem to be particularly telling parity for large problems. And similarly for connectedness, like if I tell you whether this point is connected to this point over here, you probably have a hard time, and you have to somehow emulate something sequential, but you don't see it directly. So there are certain tasks that indeed perceptrons can't solve, but probably we also can't solve. Nevertheless, this book was received very positively. For instance, by many. Here, Alan Newell wrote a review which starts saying this is a great book. And at the end, he also says, well, I should remark I'm not an unbiased witness, because I share with Pinsky in paper the common view, the appropriate shaping of computer science is the discipline field of inquiry. So this was not just about perceptrons, but it was about how to set up computer science, which was just being born in those days. And to understand that, we have to look a little bit also at the context. And the context was symbolic artificial intelligence. So first of all, one should say, in those days, I think a large fraction of all people that were doing what we now call computer science were interested in artificial intelligence in some form. People were thinking that they were not yet interested in using computers for ad placement optimization. They didn't know the problem exists, but they thought of this as a trying to understand intelligence. So maybe we're now moving back in this direction. At some point, AI was dead in science departments. Now it seems a lot of the action in science departments is again in AI, machine learning, etc. In those days, that was still the case, but people didn't agree what's the right approach. And there was this field of symbolic AI. And the one sentence definition of that is that overthinking intelligence is a process of manipulating discrete symbols. So that's some of the most famous people associated with McCarthy, Simon, Pinsky, so all very famous scientists. I mean, Simon, since won both the Turing Award, shared and the Nobel Prize for economics. So these were the giants of early computer science, of symbolic AI. And they also made some predictions, just like Will and Butts. And so Simon predicted 57 that within 10 years, a computer would jumping chess, that it would play out much longer. A computer would discover and prove the important new mathematical theorem. I think we can agree that computers have proved important mathematical theorems. I don't know whether people believe that have discovered, or maybe they can by discover. He also said we computers would provide music considerable aesthetic value. I guess a lot of people say that still hasn't happened till now. That's by 1967. So, so by and large, I think it's fair to say that these predictions were not correct. Nevertheless, symbolic AI did give birth to the science form and developed in subsequent decades. So it's certainly this symbolic view on manipulating discrete symbols helped transform computers into symbol processing systems. So computers initially were just about number crunching. I think it's a big step to view computers as processing symbols, and this is also associated with various books. I say that Matsu already had that, but certainly it was crucial for the field of science to view computers as not just about numbers. And these symbolic AI people also developed some significant early high-level programming languages like IPL and Lisp. And at the same time, digital computers became widely available, which was, of course, fit perfectly with this research program here. So perceptrons came to an end because symbolic AI was gaining momentum parallel. Many of the groups stopped doing it. Wasn't that continued for a while, but it died in 1971. A floating accident, something like that. Then people were lobbying that ARPA, or funding agency, should stop funding neural network, this guided research field. So they decided to back symbolic AI. And then the defeat of the neural networks also helped legitimize symbolic AI. There's a quotation from Simon. It says the principal body of evidence for the symbolic hypothesis is negative evidence, the absence of specific competing hypotheses as to how intelligence might be accomplished. So if you view it like this, then it's actually good to kill the other field. Then you can use it as an argument in favor of your own thoughts, and not telling that you should act like this. This is not very scientific. Well, I think that's too strong a statement, but this is just to explain that if research fields grow or shrink, you always have to view it in the context of other things going on, and the research is full of people who all have their different interests and are saying different things. They might tell you that something is great and something else is bad, for reasons that are much more complex than you, because we all built our careers in science. And while we try to be as neutral and fair as possible, sometimes it's difficult to separate the interests. So machine learning was sort of then moved to exile. Relatively few groups continued doing something related to neural nets, and internet, like Canada at the time, America, Amari, Van, Rosberg, Boston. So there were various groups, but relatively few. There was this parallel development in Russia. So in Russia, at Institute of Social Science of the Academy of Sciences, they were very excited when the Rosenblatt development happened of convergence theorem, and a lot of theoretical started working these kind of problems, automatic pattern recognition systems, and did a lot of work to also develop pattern recognition algorithms that people in the West didn't hear much about. A lot of stuff was just published in Russian, but they continued. They kind of cut off, continued doing their work in machine learning, and then of probabilities came into the back door again. Once people noticed that expert systems outgrow classical AI needed to be made probabilistic. And one of the main people in this field were J.R. Pearl. This works probabilistic intelligence systems. And eventually this direction then about how the system update probabilities and connect probability to each other, etc., gave birth to Bayesian nets of graphical models, which you Pearl as the founding father. Neural networks, I already mentioned before, then at some point came back. People noticed that symbolic AI was good at some things. It was doing well at things like chess, tree search, this kind of stuff, but it failed miserably at some problem that initially thought were easy, speech and vision. So it turned out that by hand engineering things, building expert systems in logics, you can't solve speech and vision. Computing became much cheaper. And there was this group, parallel distributed processing group, formed by psychologists. So this didn't come within computer science. And also from another direction, physicists were moving into the field of neural networks. This is John Hopkins at Caltech. And they were inspired by connections between neural networks and mechanics, which is the Ising model. And then one of the major developments was also the Boltzmann machine, which also came. Also a psychologist. So and also Berezovsky is another scientist, as far as I remember. So these developments sort of were revived from outside computer science, and people discovered or rediscovered the backpropagation algorithm. It's discovered by a number of different people, and showed how to use this to train multi-layered systems. This then prompted Minsky and Pepper to have a second edition of their Perceptron book. They're probably worried about the ghost from the past coming back to haunt them. We have the impression that many people in the connectionist community do not understand this backpropagation is merely a particular way of gradient, etc. Sort of the basic limitations of hill climb. It's a little good can come from statements like, as a practical matter, gradient descent leads to solutions in virtually every case. Such pronouncements are not merely technically wrong, etc. So it's they have strong opinions about this. But actually, I recommend looking at this book. I think it's interesting to look at this, milestones in the history of our field. Now, of course, there were also important developments coming from probability and statistics, and arguably the Bayesian updating of Bayes' theorem goes back to Laplace, who applied it to celestial mechanics. Also, Gauss was interested in celestial mechanics and Wells model, etc. Some other interesting influences. Solomonov viewing very early work on viewing AIs as probabilities, and various other developments. The conferences of the field started uncertainty in AI, so this is one development to move away from the symbolic AI in 1985, Gibbs 1987, and a lot of people trying to make machine learning more probabilistic, starting McKay. Sadly passed away recently, but also a number of people who are still with us, and was also support vector machines. And maybe a little bit more about this, because that's one part of the history that I have experienced more closely. So here, Bablik initially proposed what he called the generalized portrait algorithm. In the late 60s. Or maybe mid-60s, PhD thesis, which was some kind of optimal margin perceptron rule or perceptron algorithm. And there was also this notion of positive definite kernels, which were already used in the 20th century by Hilbert, later on in statistics approximation theory by Chris Waber and others. Curiously, in this book, this used to be the Bible of pattern recognition, Tuka and Hart. Who knows the book of Tuka and Hart? So just a few. You had asked 20 years ago, everybody would have known this book. In this book, they even write about these positive different kernels at some point. They say that this their use is suggested for their mathematical beauty rather than their practical usefulness. But then people put together positive definite kernels with the generalized portrait algorithm and developed support vector machines. Or initially they were called optimal margin classifiers. This is the first paper about support vector machines. see so much detail. There one other step then later, it seems, but one later step was the development of the general kernel tricks. So at the beginning, people didn't notice that you can actually use kernels in any method that's built on dot products. And then in this paper about doing it for component analysis, we pointed this out, and people have now applied it in all sorts of domains, which provided nice methods to think we have a course about kernel analysis. I don't know, it would probably be a more theoretical course by Bernhard. But from a practical point of view, the important thing was that you can take any algorithm, make it nonlinear by kernelization, and you can also construct algorithms that are built on non-vectorial data as long as you find suitable. This was thinking for structured data that's actually the part of the process. Anyway, so then you're all familiar. One of the papers, but not the first one, in this recent revival, the second revival of neural networks, was this DeepMind paper published in Nature, where they took a neural network architecture and showed that they can learn to play a set of different Atari games with essentially the same architecture, given enough training data. And this was, even if methodologically wasn't new, I mean, they were using neural networks combined with Q learning. Was like this one, Smith, like that. Let's say 25 years ago, quite a while ago. So they put together various pieces. Maybe all the pieces were known, but nevertheless, putting them together and running things at scale, suddenly they could show something that people thought was impossible. The wider community outside machine learning noticed that something amazing is happening. And at the time, I thought about what is interesting, or what are the trends at work. I was asked to write a commentary in the same issue of that journal, and I think it's multiple things in parallel, and we are still in this development. One is high capacity machine learning systems, so systems that can learn pretty complex nonlinear function classes. Massive amounts of data. So this system I should have written that can be trained on large trainings, on large sets. Then the availability of massive amounts of data, and this can be either by simulation. So in this case, it's by simulation because they have this video game emulator that they can run very fast and modern. So you can generate unlimited data from the simulator. Or you don't have that. Often you have large data sets by human labeling, by high labels, or using like etc. Then the increasing compute power, in particular GPUs for massively parallel computation. And as I mentioned before, one of the trends was also that we look at problems that are essentially IID, or we have tricks to make them IID. So, for instance, in this problem here, in reinforcement learning, you always have this issue that if you want to do it purely online, the kind of data that you see depends on where you are in the state space, which then depends on what your current system is. It is a biased selection of kind of data that you're going to see, and people have struggled with this for decades. In this paper, what they do is that they store data and in some kind of memory, and then occasionally commute those data and retrain on so by computing. So you make it a little bit more identical distribution that data points are drawn from. So these are some of the trends at work. I'm moving towards the end of the talk. The general slides. Maybe this, as to conclude this thread about the development of computer science. So computer science is a discipline centered on programs, and a program can be written only if you have a precise model of what it should. So scientists study specification, how to specify the program well enough, and then maybe turn it into a program, and then afterwards you verify that it does what it should do, and then you're happy. And there's a crucial role in this process, of course, is played by the humans, because the human has to come up with this model or specification. And this is a non-trivial step of induction. So you look at a program, come up with a model, and then you turn it into a program. And once it's turned into a computer program, the computer can do the rest. So the rest is just pure action computation. So that was the division of labor in computer science, and that influenced how we developed that field, what was being studied in that field. And this works provided the induction step is easy enough. So as long as we look at problems for which that we can specify well enough and where we come up with programs. So chess is one such example. It's a limited world that are limited. A human can write a chess program that beats any other human. So this is doable. But if we are dealing with a complex world where maybe the humans cannot do the induction step, the structure underlying the data is too complicated, then this just doesn't work. And then in the past, that would have been outside of the domain of computer science. And I think this is the change that we're currently seeing, that computer science is starting to embrace this kind of, so computer science we do now as a more general modeling approach. And it includes things like machine learning, where we have observations rather than what. And this, for certain simple things, and by simple I mean pattern recognition and simple modifications of it, we can actually replace the induction step that used to be done by a human. And therefore, machine learning is now at science. And I should say also, intelligent systems. And machine learning is, for me, the only reasonably well understood organizing principles, the principle of intelligence current. So if we want to understand the principles, we should understand machine learning. So I also like to tell everybody they should read this book. If you haven't done that, it's kind of the original Bible of our field in some way. This is Isaac Asimov Foundation. He writes about this cast of scientists called the psychohistorians, or sometimes he just calls them psychologists. So this is set in the future, science fiction. And in this future, psychology has developed into a field of mathematics. So the greatest psychologist is Harvey Seldon, who turned psychohistory or psychology into a profound statistical science. And he writes, psychohistory was the quintessence of sociology. It was the science of human behavior reduced to mathematical equations. The individual human being is unpredictable, but the reaction of forms with large groups could be treated statistically. So this is really the essence of machine learning, what machine learning is about, and why all these companies are machine learning. They deal with human large human mobs, and they treat them statistically, and the larger the mob, the greater the accuracy. I don't know whether mob had the same connotation in those times. The greater the accuracy. Now, so we can do impressive things now. Of course, this also means that maybe some things we should be worried about. So who has seen this book? So a little more than 2.5. Maybe this is saying something about our field. And so this was written by a philosopher at Oxford, Nick Bostrom, who is kind of specializing in various ways the human race could kill itself. So he has also thought, before he wrote this, wrote other books about potential disasters that happen. And here he's thinking about what will happen if machines get more intelligent. And somehow one of the worries is that once you have a machine that's a little bit more intelligent than humans, this machine can then build something that's even more intelligent, and then we get this exponential extremely intelligent. And some people believe, I'm not sure, but some people seriously believe that once this sort of point has been passed, it would be a matter of weeks and we're out of it. I don't believe in that, but I think it's if you stay in the field, you're going to be one day journalists are going to ask you about that because they like this kind of stories. I don't want to ridicule this book. I think it's interesting. I mean, I don't share most of the judgments, but still, he's trying to do a job. He wrote this book. No, that sounds too bad. No, I mean, he seriously tried to consider all the possible paths to superintelligence. So, for instance, one of the paths for him is brain simulation. So he says there's now this project funded by the European Union with a lot of money. That's yet another discussion about this project, the human brain. Human brain project, where they say they want to simulate the whole brain and cure psychological diseases by simulating the brain. So I think that's very naive. Anyway, so one of the paths to superintelligence, for instance, could be by brain simulation. Just once you have a simulator of the human brain, you just scale it up and you build a smarter brain. Anyway, so maybe this is something we can discuss over a drink. I don't want to go into details on that, but there are some, from my point of view, some more concrete worries. This is one of them, for instance, the use of AI for autonomous weapons, so or maybe more specifically lethal autonomous weapon systems. So if you don't want to risk the life of your soldiers, then of course you would want to build robots that do what soldiers do and soldiers kill, so that robots should be allowed to kill some. So that's a worry, and so this is one of the potential dangers. So I think so. I'm not personally worried about superintelligence, but I think we should worry about some other things in our field. We shouldn't just naively think there are no consequences. So some people have argued that we are now at a stage that physicists were at in the 1920s. So physics was a sort of pure academic discipline. So that project alters the course of history. So maybe computer science is at this point now where we are starting to have a strong impact on our society. We should be aware of that. So this is one such field. But there's also lots of issues in self-driving cars, ethical decisions that are being taken by automatic systems, etc. And we're only just starting to think about this and understand this. Okay, so coming to the conclusion. This is a painting of the English artist L.S. Lowry. Some other pronounce the name. Lowry. So Lowry was doing these nice depictions of the Industrial Revolution. This is sort of full of chimneys that cars get, so somehow still looks like a peaceful scene. Historians, so there are people. Some people say we are now in a revolution. So historians distinguish two industrial revolutions. The first one was in the started in the late 18th century and then in the first half of the 19th century, and that was dominated or triggered by the steam engine, by water power. So it was about how to generate energy at an industrial scale. Second one was about 100 years later, and this was driven by electrification. So turning one form of energy, electric energy, can transport much more easily, scales up things even further. And if we think about it broadly, both these revolutions are about how to generate and convert and process forms of energy. And of course, generation, you have to take the grain of salt because physicists tell us you cannot generate energy. It's conserved. But you can convert and process energy. So you take such little pieces of energy for many things and put together, and you have a lot of energy. Now, in the current revolution that we are in, this has been called the digital revolution, or more recently, the big data revolution. But I tried to explain that argue that it really started already in the mid-20th century with the name of cybernetics, because that's when people understood that energy is now replaced by information, and we should understand what happens with information. And like information can be processed by people, but if you want to do it at an industrial scale, you need machines to do it, and machines are computers. And if you want to do it intelligently, you need to have maybe more intelligent machines. You need stuff like machine learning and AI. So the current revolution is really the same thing, just replacing energy by information. It's probably the case, although that's debated in physics, that information is also a conserved quantity. So maybe you cannot generate it. There are some discussions about what happens if you throw something in the black hole. Does the information really vanish, or is it still there, or maybe it gets emitted while the stuff wasn't. But some people think that actually conservation of information is even more fundamental than conservation of energy. But you can do things like harvest little bits of information. You have from each user, and you have different users. Then you can do something. You can extract some bigger, maybe more useful information from it. And this is what machine learning is doing in the industry. So I think with this general context, I would like to put this talk. Thank you very much. So it's, it's not so much a typical lecture, so I won't be upset if you don't ask questions, but we can discuss a bit. Okay.
So to address the title of the talk, what is machine learning?
Okay, so look, I like to answer this with one anecdote. So I remember so my PhD advisor was Planck, and he told me the story how they published their first big results about the BC dimension, and they proved you can use the BC dimension to bound the growth function. And this was a big thing, and people were quite excited about it. So, for instance, once it was published, there was an American mathematician, probabilist at MIT, Dudley, who wrote a review, mathematics or something like that, where he called this result shocking. Anyway, so Wapnick, Germany, they found this result. They noticed immediately this is something big, and then they wanted to publish it in the proceedings of the Russian Academy of Science. And there were two little guys, maybe I think already had graduated. Japanese might have still been a student. So they wanted to publish it in the statistics section of the most prestigious journal in Russia. And then, so they had to go and see, I don't know, had to go through some important academician, and they ended up being sent to Nedenko, a probabilist. And then Nedenko told them, I think this might be good work, but we can't publish it in statistics. And they said, well, but this is, we're not statisticians, but what we did is statistics. This is a generalization of the Ivinko-Cantelli theorem. It's a classical theorem of statistics. I think this is, with all respect, we think this is good work. So if this is not statistics, what is statistics? And he said, well, statistics is what I'm doing, what my students are doing, what this guy is doing and his students. And so Wapnick told me he was quite upset when he heard that. But then later he said, now he understands that this is actually correct. So a field is defined by stuff that are doing. And maybe another anecdote. So artificial intelligence, you could also ask, what is artificial intelligence? And I remember I met a guy at a conference, famous AI, 15 years ago, very famous AI guy doing fuzzy logic. So he was classical AI augmented with fuzzy logics, and we were at the same conference, and we were sitting together at the conference dinner, and we had some kind of argument about fuzzy logic. Somehow I didn't like fuzzy logic. I was trying to tell people that it's the probabilities. And so we had a bit of a contentious discussion at some point. But look, at least we can agree we both do AI. I always thought of machine learning as AI. And then he was laughing loud and said, "Hey, you're not doing AI." And nowadays, if you ask people, like almost everybody doing machine learning would call themselves AI, or even if you ask people what is AI, really first thing people tell you is machine learning. So it depends very much what the communities do. I think there's no good logical definition of what is the field. So I think now machine learning is mostly what machine learning people do, and they're mostly now in computer science departments. And so not long ago, there were very few computer scientists doing machine learning. So probably this is also changing the field. At some point, I don't know, 10 or 20 years ago, there was still some contentious debate as to whether machine learning should just be a subset of statistics. So when machine learning was just, we were technically a bit underdeveloped, and some statisticians were entering the field, Jerry Friedman, Barney, Hasty, etc. And there was this Brian Dupree was this feeling that maybe we're just a subset of statistics, and these guys are technically stronger than us, and we should just properly statistically. But nobody talks about that in our machine learning, at least in that part of computational statistics. So it's all about the community that do it. So maybe that's not a bad set. So we have a slightly longer break. So thank you.